If you design a system and just tell it to minimize the difference between its current state and its future state,
Mhm.
the most mathematically efficient thing it can do isn't to actually learn the complex laws of physics.
Right. No, that would take too much effort.
Exactly.
Hmm.
I mean, the absolute most efficient thing it can do is to just close its eyes, turn the universe into a single, unchanging constant, and then proudly report an error rate of exactly 0.
It's the ultimate lazy shortcut.
It really is. And if you're in the trenches of training joint-embedding predictive architectures, GPs, then you definitely know this lazy shortcut by its real name, which is representation collapse.
The bane of the architecture, yeah.
Welcome back to the deep dive. We know you live and breathe machine learning and data science, so today we're skipping the fluff and getting right into a major breakthrough. We are unpacking a paper titled LeWorldModel, Stable End-to-End Joint-Embedding Predictive Architecture from Pixels.
It's a fantastic paper by Maes, Lidec, Scieur, LeCun, and Balestriero.
Yeah, and the core innovation here, the reason this matters for your own research, is that it presents a JEPA that actually trains stably end-to-end straight from raw pixels. And it does this on a single GPU using only 2 loss terms.
Which is, frankly, unheard of in this specific domain.
Right. But to understand why a 2-term loss is so revolutionary here, we probably need to mathematically diagnose that persistent plague of JEPAs we just mentioned, that representation collapse.
Yeah, we have to start there because the problem of collapse is just fundamental to the architecture itself. The core premise of a JEPA is to take these really high-dimensional observations like, say, pixel frames from a robotic arm and encode them into a compact, low-dimensional latent space.
Makes sense so far.
Right, and then you train a predictor to model the temporal dynamics. So given the current latent state and some action, the predictor's job is to output the latent representation of the next state.
And the standard way people optimize that prediction is just using mean squared error, right? Good old MSE.
Exactly. You want the predicted next embedding to match the actual next embedding that the encoder produces. But here is the fatal flaw. When you jointly train the encoder and the predictor end-to-end, the network discovers that trivial solution we were laughing about earlier.
It finds the lazy way out.
Yeah, the gradients optimize the MSE perfectly by just pushing the encoder's weights to map every single possible input to an identical constant vector. So then the predictor just outputs that exact same constant. The MSE drops to 0, the latent space is completely destroyed, and, well, the model has learned absolutely nothing about the environment.
Which is incredibly frustrating.
Yeah.
And it forces practitioners into these truly painful engineering compromises just to keep the latent space from imploding. I mean, look at the PLDM baseline, the predictive latent dynamics model.
Oh, yeah. PLDM is a perfect example of how the field has historically just patched this flaw with Band-Aids.
Right. Because PLDM derives its anti-collapse mechanism from the V-trig criterion variance, invariance, and covariance regularization. But because PLDM is dealing with sequences in a predictive architecture, standard V-trig just isn't enough.
No, not at all.
So they pile on temporal similarity regularizations, temporal variance, temporal covariance. It's a massive, chaotic 7-term loss function.
And the worst part is, those terms actively fight each other in high-dimensional space.
Yes. The standard variance term is trying to push batch embeddings apart to prevent collapse.
Right.
But then the temporal similarity term is trying to pull adjacent time steps together. So if a robotic arm moves just a fraction of an inch, the variance gradient screams, push these apart, they're different instances.
Well, the temporal gradient screams, no, pull them together, they're adjacent in time.
It's a total catastrophe. You get this massive gradient conflict. And to balance that contradiction, you're forced into an O of n to the 6th hyperparameter grid search.
Which is just brutal.
It's a polynomial time nightmare just to keep the model breathing.
It really is. And, the main alternative hasn't been much better. The other mainstream approach is DynoWM. And they avoid the gradient conflict entirely by simply refusing to train the encoder.
The freeze and pray method.
Basically, yeah. They just freeze a pre-trained DynoV2 vision encoder and only train the predictor. And sure, freezing the weights guarantees the encoder won't collapse, but it completely bounds the model to the expressivity of its pre-training distribution.
Because it can't learn anything new about the specific environment.
Exactly. If your specific robotic task involves recognizing translucent objects or really specific textures that weren't represented in DynoV2's massive training set, that information is just dropped. The frozen encoder ignores it, and the predictor never even gets to see it.
So the field has basically been trapped, right, between the heuristic instability of PLDM and the bounded expressivity of DynoWM.
That's exactly where we were, until LeWorldModel, or LeWM.
Let's get into the elegance of this solution because it's so incredibly lean. Instead of piling on regularizations or freezing massive foundation models, LeWM uses this tiny architecture paired with a strict mathematical prior.
It's remarkably small.
Yeah, the encoder is just a vision transformer tiny, a VT tiny, weighing in at only 5 million parameters. And the predictor is a 6-layer transformer with 16 attention heads, adding another 10 million. So we are looking at a 15 million parameter model.
A fraction of the size of the alternatives. And the engineering choices within that 15 million parameter architecture are highly deliberate.
How so?
Well, for example, the paper highlights a really critical issue with standard layer normalization. They found that applying standard layer norm at the final VIT layer actually prevents their anti-collapse objective from being optimized at all.
Oh, interesting. Because layer norm normalizes across the feature dimension, right?
Right, which couples the features together. And that coupling distorts the isotropic target of their regularization. So to fix this, they take the CLS token embedding from the last layer and pass it through a 1-layer MLP with batch normalization instead.
Because batch norm normalizes across the batch dimension, so it keeps the individual features independent.
Exactly. It preserves the structure they need.
They also handle the injection of the action vectors really carefully, don't they? I noticed they use adaptive layer normalization, or ADLAN, at each predictor layer, but they initialize the scale and shift parameters to 0.
Yeah, the 0 initialization is crucial. By doing that, the action conditioning block initially acts as just an identity mapping.
Right.
So the model starts out by learning the unconditional temporal dynamics of the environment first. Then, as training progresses, it gradually lets the action gradients flow in.
Which makes sense, because if they didn't 0 initialize, the high variance of those randomly initialized action embeddings would introduce massive noise. It would totally destabilize that carefully regularized latent space early on.
Absolutely. So the architecture sets the stage, but the actual optimization objective is really where the mathematical innovation lies here. The training loss for LeWM is just LPRED plus lambda times SIGREG.
Just 2 terms. LPRED is the standard MSE for next-embedding prediction, and the anti-collapse mechanism is SIGREG, which stands for the Sketched Isotropic Gaussian Regularizer.
Now, testing for a Gaussian distribution in a high-dimensional latent space is a notoriously difficult mathematical problem.
Oh yeah, the curse of dimensionality. The volume of the space just grows exponentially, your data becomes incredibly sparse, and standard normality tests completely fail.
Right.
It's like trying to understand the complex shape of a high-dimensional point cloud, but you only have a 1D lens to look through. So what do? You take multiple 1D shadows of that object from random angles.
I love that analogy.
Thanks. And if every single shadow looks perfectly like a standard Bill curve, you can mathematically deduce the shape of the entire high-dimensional object.
Yes, and the beauty of relying on those shadows is that it completely bypasses that curse of dimensionality. By projecting the high-dimensional latent embeddings onto m-random unit norm directions on a hypersphere, LeWM reduces the whole problem to just a series of simple 1D distributions.
It's so clean.
It is, and once it has those 1D projections, it optimizes the univariate Epps-Pulley test statistic on each one.
And the mechanics of the Epps-Pulley test are fascinating for you math nerds out there, because it doesn't rely on binning data into histograms.
Which is great because binning always loses information.
Exactly. Instead, it uses the empirical characteristic function, or ECF. And the ECF is essentially a Fourier transform of the probability density function. It maps the distribution into the complex plane, which gives it this unique characteristic footprint.
Right.
So the Epps-Pulley statistic basically measures the weighted integral of the squared difference between the ECF of our projected 1D latent data and the theoretical ECF of a perfect standard normal distribution.
It's brilliant because it provides this really elegant continuous measure of non-normality. And once you calculate the Epps-Pulley statistic for all those 1D projections, the math relies on the Kramer-Wold theorem.
Ah, right, the Kramer-Wold theorem.
Yeah, which states that if all one-dimensional marginal distributions of a random vector match a specific distribution, which in our case is a standard normal, then the full joint high-dimensional distribution must match the target isotropic Gaussian.
So by anchoring the anti-collapse mechanism to that theorem and the Epps-Pulley test, all that old baggage just vanishes. No more stop gradients, no exponential moving averages, no convoluted temporal regularizations fighting each other.
Gone. All of it.
The hyperparameter search space collapses from that O of end of the sixth nightmare down to literally a single parameter.
Yeah.
Lambda. the weight of the sig-rig loss.
Yeah, you can find the optimal lambda using a simple O of log n bisection search.
Which is incredible for you as a practitioner. The result is a highly stable end-to-end training pipeline that runs easily on a single GPU.
But, theoretical elegance is satisfying, sure. But the real practical test is how this tiny 15 million parameter model actually performs when you drop it into a model predictive control scenario.
Right, let's talk about the planning efficiency. The authors evaluate this by setting up latent planning using the cross-entropy method, or CEM.
Yeah, CEM is a zero-order optimization algorithm that's widely used for planning. The way it works is you sample a massive pool of candidate action sequences from a parameterized distribution, then you roll them out in your learned latent world model and evaluate the predicted cost of reaching a goal state.
And then you select the top K elites, right?
Exactly. The action sequences with the lowest cost. You refit your sampling distribution to those elites, and you iterate this until the solver converges on a solid plan.
But because CEM requires thousands of simulated rollouts, the forward pass efficiency of the world model is absolutely critical. And since LeWM encodes observations using a VT-tiny, it processes roughly 200 times fewer tokens than the heavy foundation model approach of DINO-WM.
200 times fewer.
Yeah. So the efficiency gains in the planning loop are just massive. LandWM executes a full planning sequence in 0.98 seconds. DINO-WM takes 47 seconds.
It's almost unbelievable.
A 48x speedup. That pushes the architecture significantly closer to real-time control capabilities.
And it achieves that speed without sacrificing task performance, which is the crazy part. On the push-T benchmark, which requires complex 2D manipulation of a T-shaped block, LandWM reaches a 96% success rate under a fixed compute budget.
Wow.
It completely crushes the heavily regularized PLDM, which stalls out at 78%, and it easily beats the frozen DINO-WM, which maxes out at 74%.
So an end-to-end trained model with a strict isotropic Gaussian prior is fully capable of capturing the complex dynamics required for precise manipulation.
It is.
But looking through the data tables in the paper, there's a glaring anomaly that we have to talk about.
Ah, yes, the two-room anomaly.
Yeah. The authors test the models on various environments, and one of them is the two-room benchmark.
Right.
Now, this is an incredibly simple navigation task. It's literally just moving a point mass between two rooms.
Super basic.
Right. Yet in two-room, LeWM only hits an 87% success rate.
Yeah.
Meanwhile, the baselines perform flawlessly. PLDM gets 97%, and DINO-WM gets a perfect 100%. So my question is, why does this highly advanced, mathematically sound model actually fail on the absolute easiest task in the entire suite?
It's a great question, and that failure really exposes the primary limitation of the sig-rig prior. It all comes down to the concept of intrinsic dimensionality.
Yeah, back that.
So in a complex environment like push-T, the visual data has a high intrinsic dimensionality. There are complex spatial relationships, rotations, physics at play. That kind of complex manifold naturally maps very well to a high-dimensional isotropic Gaussian distribution.
Right.
But the two-room environment is fundamentally different. The data there is extremely simple. It essentially boils down to just 2D coordinates. Its intrinsic dimensionality is incredibly low.
So forcing an intrinsically 2D manifold to expand and perfectly populate a high-dimensional isotropic Gaussian actually breaks the representation.
Exactly. The encoder is forced to inject noise or artificially curve the latent space just to satisfy the EPS-Pulley test and spread the data out. The mathematical regularization is actively working against the fundamental simplicity of the environment.
That is fascinating. It demonstrates that while the Cramer-Wald theorem and the sig-rig loss are incredibly powerful, they operate on a fundamental assumption.
Right. They assume the underlying environment possesses enough inherent complexity to actually populate the target distribution meaningfully without distortion.
Okay, so we've established that LeWM can navigate a complex space mathematically. It plans 48 times faster, handles high-dimensional tasks. But there's a massive difference between mathematical optimization and actual physical intuition.
A huge difference, yeah.
Does this latent space actually understand the physical reality of the blocks it's moving? Because keep in mind, there is no explicit reconstruction loss here. It's not being told to recreate the raw pixels, and it's not receiving a reward signal from the environment.
It's completely reward-free. And the authors actually investigated this physical intuition using linear probing.
Oh, yeah.
They froze the linear representations and trained simple linear classifiers to predict ground truth physical quantities directly from the latent embeddings. And they found that the model accurately tracks positional data like the exact X and Y coordinates of the robotic end effector and the position of the blocks on the table.
So the continuous physics of the scene are highly preserved in those discrete embeddings.
They are.
Though, to be fully transparent regarding the baseline comparisons, DNO-WM still holds an edge on dynamic properties.
It does, yes. For tracking properties like joint velocity or the specific yaw of the end effector during a rotation, DNO-WM performs better.
But the underlying mechanics kind of explain why, right?
Definitely. I mean, DynoV2 was pre-trained on 124 million diverse images. So it has this massive foundation of visual priors that naturally encode rotational and dynamic features before it even sees the robotic task. LeWM, on the other hand, is learning those physics entirely from scratch, utilizing only a highly restricted offline dataset of that specific environment.
Right, so the fact that a model learning from scratch can build an accurate positional tracker without ever being explicitly programmed to understand position is remarkable in itself.
It really is.
And this leads directly to the surprise evaluation in the paper, which operates almost like a violation of expectation test used in developmental psychology.
Yeah, I loved this part of the study. The researchers artificially injected physically impossible events into the visual trajectories.
Yeah, they would take a standard rollout and suddenly edit the frame so a block instantly teleported across the screen,
Right.
or the agent's color abruptly changed.
And then they measured the mean squared error of the predictor when it was forced to process that impossible transition.
And the model's prediction error spiked massively. It was mathematically surprised. It hasn't just memorized sequences. It has generated an actual intuitive physics engine within its latent space.
And that intuitive physics engine exhibits a deeply fascinating emergent property that links back to neuroscience. They call it temporal straightening.
Temporal straightening. It's like how biological brains represent complex, highly nonlinear temporal dynamics in the physical world as smooth, straight trajectories in their internal representation space, right?
Exactly. Because it makes predicting the future computationally cheaper. It's much easier to predict the next state if it's just a straight line ahead of you.
Right.
So to test if LeWM developed a similar mechanism, the authors measured the cosine similarity between consecutive latent velocity vectors over the course of training.
And a cosine similarity approaching 1 means the latent velocity vectors are pointing in the exact same direction. Successive temporal states are forming a straight line.
And the data shows that as LeWM trains, its latent trajectories do become increasingly straight. The transition from time t to t+1 to t+2 evolves linearly in the representation space.
Which is amazing. But the profound irony here is that the baseline model, PLDM, uses explicit temporal smoothness loss terms. It is mathematically programmed to penalize non-smooth latent trajectories. Yet LeWM, which has zero temporal regularization, achieves significantly higher temporal straightness than PLDM.
It's a textbook example of emergent behavior driven by independent constraints.
How so?
Because LeWM applies the sigreg regularization independently at each individual time step to enforce an isotropic Gaussian. It naturally converges toward an emergent temporal collapse.
Ah, I see.
Yeah. Without temporal constraints forcing the embeddings to behave, the transition between states simply follows the path of least mathematical resistance. And the path of least resistance is a straight line.
And think about what that means for the CEM planner we talked about earlier. CEM is sampling thousands of action sequences and rolling them out. If the latent space is highly nonlinear and warped, those elite samples might just fall into local minima, and the optimization fails.
Right.
But a linear topology gives the zero-order optimization of CEM an incredibly stable, predictable, and well-behaved space to navigate. The unsupervised representation naturally optimizes itself perfectly for the downstream control algorithm.
It all just clicks together perfectly. The LeWorldModel architecture proves that reward-free, task-agnostic world models do not require massive foundation models to capture complex dynamics.
Right.
And furthermore, they do not require brittle, multi-term heuristic loss functions that trigger endless hyperparameter tuning. By anchoring the optimization to the Cramer-Wold theorem and applying a strict isotropic Gaussian prior through 1D projections, we get a highly stable 15 million parameter model.
It trains end-to-end on a single GPU, avoids representation collapse entirely, and accelerates planning by orders of magnitude compared to foundation model alternatives.
It's a massive step forward.
It really is. But the architecture also leaves us looking directly at a massive unresolved hurdle, doesn't it?
It does.
Because LeWM, for all its mathematical elegance, still relies on offline datasets that include perfect action labels. It auto-regressively predicts future states by conditioning the predictor on the specific known actions taken by the agent. But in the real world, Action annotations are expensive.
Very expensive. They require precise instrumentation, sensors, or exhaustive human teleoperation.
Which points toward the next necessary evolution of this JEPA framework. The real frontier for you out there is eliminating the reliance on action labels entirely.
Imagine modifying the predictor to utilize inverse dynamics modeling, where the model infers the latent representation of the action directly, just by observing the transition between the current state and the future state. Consider what it would require, mathematically, to design a loss function that allows an architecture to learn the physics of reality simply by watching unannotated video, deducing the physical mechanics without ever being explicitly told what action caused the change.
A model that doesn't take the lazy shortcut of closing its eyes to a constant universe, but instead opens its eyes and maps the mechanics of reality purely by observing the flow of pixels. Something to think about for your next project.